I just got a nice message saying the meeting's being recorded. Okay, so that's the most common way that gliders now fly cross-country worldwide. Just move on to the next slide. Another way, and this is in fact how gliding started out 100 plus years ago, is to use updrafts on ridges. Now, this is a photo that I took. It's in the mid-north. No, it's not in the mid-north. It's in the Flinders Ranges in South Australia. And that picture and the mountains in the background there are actually Wilpena Pound. Now, this wasn't taken on the flight on 27th November. It was actually taken last September, but it shows you a couple of things. Firstly, it shows you a nice ridge here. So this is the southwestern face of Wilpena Pound here. On this day, the wind was blowing from the southwest, which is actually from the bottom left corner of the picture here. And then along this entire length of the ridge, you get air rising up along the face of that ridge. And of course, you can fly up and down that all day and stay in the air, as shown by this diagram on the left here with the rising air along the face of that ridge. I'll give credit to this diagram and the one that's on the next chart as well from the Darling Downs Soaring Club. That's where the diagram came from. Of course, if we're trying to fly cross country, that's a bit limiting because you're going to need a very long ridge if you want to fly 1,000 kilometres. It has been done, but not in Australia. Because if I was flying along this ridge here, you fall off the end before too long, and then you have to find some other way of staying in the air. Okay, another way, and this is how I got so high. So this photo was actually taken from about 17,000 feet last September. And I got that high by using atmospheric waves. So an atmospheric wave, or a lee or standing wave, is where you have a ridge, such as we just talked about. And if you have a stable atmosphere above that, then you have a wave formation that forms downwind of that obstruction or that ridge or that mountain. So that goes up over the ridge, comes down, bounces back up again. And this section here, where this rising air is the primary of the wave, possibly downstream from that there'll be a secondary and a tertiary and so on in a wave pattern. We can often get lenticular clouds associated with those same conditions. And in fact, this is quite important because we were talking here a little bit, we'll be talking here a bit about the technology and how gliding is actually pushing the technology in aviation. So there's a project called the Perlin project, sponsored now by Airbus Industries. So they're obviously very interested in these sorts of technologies. They've got a high performance glider, which they flew in Argentina for the world altitude record in a glider about 3 years ago, I think it was 2018, and got to a height of 76,000 feet, which is just a ridiculous height. Given that airliners are flying generally 30 to 40,000 feet, they're twice as high as your typical airliner. So that really is high. They're shooting for 90,000 feet. So some of this technology really is pushing the boundaries of what's possible from a materials point of view, from an aerodynamics point of view, and also from understanding what actually happens in the atmosphere. Okay. So the picture that you can see part of there is me on Aerotow. So that's my glider with me flying it a few years ago. You can see a rope attached to the nose. So that's how I get in the air. So I'm using another aircraft to tow me into the air. It's also possible to use a winch. I don't tend to do that these days, but I have many times in the past to climb using a cable off a winch. Okay, so you get into the air and we get our initial height, which might be, say, 2,000 feet. Find some lift, such as shown on the diagram here, cruise on, lose height as we do it, find more lift, cruise on, making cross-country distance, which is similar to what I explained before. Now, I did a lot of that on this flight in question, but it was a little bit more than just that, which is what I'll show, I think it's on the next slide. No, it's not. It's a slide in a moment, but I'll get to that. This is a plot which shows the altitude for the flight, starting at about 10 AM back here and going through to 8 PM. So that's the 10 hours of the flight. right, altitude versus time. And the brown there shows the terrain that was actually underneath me. So you can see it was rather a struggle early in the flight, but you can still see the trend. So this here, where my cursor is in the bottom left, is my initial launch, bit of a descent till I find my first climb up, glide, climb, glide, etc. for the remainder of the flight. But you can see this early part of the flight was a real struggle, low altitude, very slow progress. In fact, it took me 2.5 hours to do the first 150 kilometres, which is actually pretty common in doing distant flights. And I'll explain why it was such a why it was so necessary on this particular flight when I get to that, talking about the challenges of flying from the site of Gawler. The other thing to note from this is that peak is 15,000 feet, roughly, up here. And I spent more than 6 hours above 10,000 feet, never going below 10,000 feet. Up at those sorts of heights, above 10,000 feet, we need oxygen because the air is pretty thin up there. So I was on supplemental oxygen right through that period. So they're the three most common forms of lift, but quite a bit of what I actually did on this flight was not one of those common forms of lift. There's another one which is a convergence between airflows, which can be caused through various means, but a fairly common one is a convergence between an offshore wind and an onshore wind caused by a sea breeze, which is what's shown on this diagram here. So here we have thermals, which lift the air over the land here. As it does so, that air gets replaced by maritime air coming in from the right of this picture here. And where you get a convergence between this incoming air and the offshore wind here, you get a linear feature. You can often see that around Adelaide. We often get a sea breeze early afternoon. And when you do, and it tends to happen over the hills, you can get a line of clouds. That's where that convergence line is. So as glider pilots, we can fly along that line of cumulus and potentially we could actually just cruise without needing to climb, or more likely is that the lift is stronger along there. We can get much better, faster speeds cross country along that. So I'll show you the next slide, which is the opening slide that I actually showed. So this is on that day, taken at about 5 p.m. It's in the mid-north facing south. So the town of Jamestown, which was actually my first turn point on this flight, is off to the left of the screen. We have the Gulf of St. Vincent to the right here. So this area where there's no cumulus out to the right is the maritime air, so the sea air. And then you have the convergence between the wind, which was predominantly coming from the left here, meeting the sea air, and then this linear feature. Now, on this particular day, that extended, and I looked at the satellite images afterwards, extended from north of Port Augusta to virtually Tasmania. So this is, 2,000 kilometres long. We call it a highway in the sky as glider pilots. It really is fantastic just to follow this as we're going along. And that's basically what I did for the majority of the flight. Photo here is taken at 12,000 feet and the cloud base is about 15,000 feet. One of the advantages of having a big cloud base like that is that the air is less dense higher up, which means you can actually cruise faster ground speed. But the other advantage is if you're getting very high, then of course you can glide quite a long way before you need to climb again. So there's several advantages in actually staying high. And it feels good to be up there anyway.
Peter, I got a couple of questions for you. Timothy Byrne wanted to know, did you carry water ballast and how did that improve your glide?
Yes, I did. And we'll get to that in a couple of slides' time when I'll talk about the technology of the gliders and why water ballast is important.
Okay, and there was one other question. It was just what size oxygen bottle did you use above 10,000 feet?
I think its capacity is, I'm not sure. A fairly standard capacity, 3 or 4 litres or something like that of high pressure. High pressure oxygen, 3,000 psi or just under.
Excellent, thank you.
But using even though you're at altitude for a long period of time, it's only supplemental and you're actually not using a lot of oxygen, and that size cylinder, oxygen cylinder, will last a lot longer than 6 hours at those sorts of altitudes. Okay, so talking about the technology, which is how we'll get us onto water ballast. This is what I was flying. So this is my glider. It's called an ASG 29, built by a company called Schleicher in Germany. Most of the gliders in the world are made in Germany, with some made in Poland and more recently South Africa. There are a few smaller manufacturers around, but traditionally, and as a result of the Second World War, actually, when gliding in Germany took off because they didn't have any other form of aviation after the Second World War. So most of the gliding manufacturers are based in Germany. Anyway, the glider, when I bought it, was state of the art. Unfortunately, technology moves on and it isn't anymore. It's been overtaken now by a number of later models from this manufacturer and other manufacturers as well. But even then, the newer gliders are only maybe 1 or 2% faster, so not by a huge amount. That photo there is of me landing, not on this flight, but a few years ago, which is why I'm so close to the trees. It was the final turn on to final before I was coming into land. And you can see in that photo there that I am actually dumping water ballast there as well. I'll go right into the terms of the technical data here. I'll go right down to the bottom where it says best glide ratio 50. So that's 50 to 1, which means that from an altitude of 1 kilometre, so that's 3,280 feet, it will glide 50 kilometres, which is a long way. That's pretty astronomical. But actually, gliders have been able to do those sorts of figures for a long time, for decades actually, particularly the gliders with a longer wingspan. But what's changed in recent years is the speed that the gliders can actually get that glide ratio at. And in particular, when we're cruising at quite high speed, and we want to be able to have a very good glide ratio, which is a lot less than 50. It's probably more like 30 or 35 to 1 at very high speed, because that's where we spend most of our time when we're actually going cross country. I'm not sure if I mentioned it before or not, but we're climbing on a good day something like somewhere between 10 and 30% of the time, and the remainder of the time we're actually cruising. So the cruising is a really critical part of the flight. Which brings me on to the water ballast. You'll see here that this is the technical data for the aircraft, and I was full for the flight. So we carry a bit over 200 litres of water ballast. Now, normally in aviation, water ballast is a bad thing. You don't want to be as light as possible to minimise the amount of fuel you use. But in gliding, the fuel we use is free. It comes from the atmosphere. So if I'm fairly light, in other words, I have no water ballast on board, and I'm climbing in a thermal of, say, 800 feet per minute. If I then somehow manage to put 200 litres of water in that glider in the same thermal, then it will climb a little bit less. Might only be 750 or 700 feet per minute. But that's not going to make a lot of time than the time spent climbing, and we're only spending somewhere 10 to 30% of the time climbing anyway. Most of it's cruising. So the real advantage is that it enables us to cruise much faster at the same sink rate as a light glider. Now, if we're trying to fly 1,300 kilometres, of course, you need to make good speed across the ground. I did that flight in 10 hours, so that's an average speed of over 130 kilometres an hour. Some of which, of course, stopped because I was circling in lift, so the rest of that is actually in the cruise. So some of the advances in technology in recent times is being able to get what's called the wing loading, which is here in this glider, 57 kilograms per square metre, as high as possible. That enables us to cruise faster. So they do that by either having a heavier glider, this one's limited to 600 kilograms, or having a smaller wing area, therefore the loading on the wing in kilograms per square metre is higher. So some of the new gliders have maximum wing loadings above 60, which means they are a real rocket in the stronger conditions. Of course, they need some stronger lift to actually be able to climb at those sorts of wing loadings. So from a designer's point of view, they need to firstly have the structures designed because they're very long, thin wings, and they're pretty heavy when you fill it up with water ballast. So they need to be very strong. So they're using carbon, Kevlar, those sorts of materials in the wings, and various composite structures. So the composite structures have evolved a lot over recent years, but what's really given it the main performance gain in gliders in recent years is the numerical modelling of aerodynamics, in particular computational fluid dynamics. So this is where we're actually, I'm not doing it, the designers are doing it. They're designing the wings numerically rather than before where they tended to have a bit of a wild guess and do it in wind tunnels, but designing them to be as efficient as possible. So even in this glider, designed something like 15 years ago, the wind is laminar over almost the entire bottom surface of the wing up to a few centimetres from the trailing edge of the wing. Anywhere where the airflow over the wing is turbulent generates drag, so that's a bad thing. So if they can get that back as far back on the wing as possible, then that increases the glide ratio, reduces the drag, increases the glide ratio. On the top of the wing, it breaks away and goes turbulent somewhat forward of that point, but there's been big improvements in recent years in terms of the CFD and the performance of the glider wings in particular. Right, moving on to the specifics of the flight itself. Now, I think a reasonable number of the people that are actually listening tonight and watching this are pilots, and all the pilots will recognise this chart, which is a VNC or a visual navigation chart. Gawler is down here on the bottom of the chart, and you can see, well, if people are familiar with these charts anyway, is that we are in this pink or this restricted airspace here. So we're actually within the restricted airspace for the Edinburgh RAF base. And that limits our options, particularly midweek, as this flight was on a Friday. The only real way I could actually get out to start the flight was down this narrow corridor out to the northeast. Out to the east here, we have the Adelaide Hills, which is not something you want to fly over particularly low. And in any case, the thermal activity starts, it takes a bit more time on the plains out to the east here. It takes a bit longer to get going. So early in the day, the thermals weren't starting there. So I was forced to kind of head out to the north. And one of the problems of doing that is that the only conditions where we can fly a long flight like this is when we have a northerly wind, because that's on those days where you get the higher temperatures. So we're forced to go out to the north or northeast into a headwind, and fairly early in the day. The reason it needs to be fairly in the day is, of course, I was trying to maximise the distance I could fly, and the thermals are only there when there's a bit of heat in the day. So they start at some time in the morning, 10 a.m, 11 a.m. perhaps, and run through to sometime before sunset. So early in the day, there's not a lot of heat. The thermal updrafts are fairly weak. It's hard to make progress, which is why it took me a long time to do the first 150 kilometres. It's actually a challenge with distance flying to know when to take off, which actually comes down to the weather modelling, which I'll talk about in a minute. Because if you take off too early, it'll launch too early, then before you know it, you're back on the ground having not found any thermals because they're not there yet, they haven't started yet. If you take off too late, then you've wasted some of the day. And in terms of taking off too early, there are several flights where I've been quite embarrassed, declared 1,000 kilometres and find myself back on the ground after about 5-10 minutes, which is a little bit embarrassing. So it is important to actually get the time to take off as accurate as possible. Which comes down to weather modelling. Now, this analysis chart here shows the situation on that day, 27th of November. And I'll talk about, I guess, how we used to do things and how we've evolved now in terms of the modelling of the weather. So this shows the pressure pattern on that day. The most obvious feature is this trough line, which was running, was actually a little bit further than that, further north than this is showing. But anyway, ran across southern South Australia, down into Victoria, down into Tasmania. So that's where that convergence line was. Was the trough line there, and the convergence line happened to match that. In days past, what we did, we'd look at this synoptic chart, or prognostic chart. We'd look at forecast maximums from Bureau of Meteorology. We'd look at observations, in particular the atmospheric sounding. So that's the sounding of the temperature and the dew point of the air and wind with altitude, and use some heuristics and basically guess when the thermal was going to start, how strong they were going to be, where the best regions would be to fly. It's way easier to do that than it used to be. And in particular, what's changed more recently is a number of soaring specific atmospheric weather models. I'm going to talk about SkySight. There are others. This is not the only one, but it's certainly the one that I believe has the best technology, and it's the one that I actually use. So in terms of atmospheric modelling, it's not a new field. And in fact, there's a worldwide model called GFS. I think it's Global Forecasting System or something like that, which has a fairly coarse grid. It's worldwide, has a fairly coarse grid and a fairly coarse time interval, but at each grid point and time interval, it comes up with models and comes up with a chart such as this chart that's here. So this chart on the vertical axis is pressure. Now, because pressure decreases with altitude, that correlates to altitude, and then temperature across on the horizontal axis here. Red line is the temperature, green is the dew point, and blue is the wind. Now we can extract an awful lot of information from this prediction. So this is, remember, this is for one location at one point in time. We can predict the height that thermals are going to go to, the strength of thermals, the shear in thermals, cloud base for cumulus clouds, higher layers of cloud, overdevelopment, rain, wave, you name it, you can extract a lot of information from this one diagram. If you extrapolate this to every location on a fairly fine grid and lots of time interval with time increments during the day, then you have tens of thousands of these over a potential flight area, and humans, of course, can't make sense of any of that. And that's where these models actually come in. So what SkySight does is it takes in Australia, there are other sources elsewhere in the world, but it takes GFS and interpolates the data points onto a small grid and also small time steps at 30-minute time steps during the soaring part of the day, daylight hours of the day, and presents that information in a way that's actually usable for us as glider pilots. Now, this is a pretty busy slide, and it shows the main interface to SkySight. SkySight, by the way, is a subscription service. And I actually should just talk a little bit about the history of it. There have been for some time soaring specific weather models, but they had their limitations. And Matthew Scudder, who was originally from South Australia, now based in Brisbane, and also a computer scientist, had a keen interest in modelling of the weather and developed SkySight to assist him and others. It's now available by subscription. And he's used it to really good effect in competition flying, and in particular for the World Gliding Championships which would happen to be in Australia in 2015. He used it to assist him in winning that World Championship. So it really was leading edge and still is. It's evolved a lot since that time. So some of the parameters that are really, really important for us to look at to predict where the conditions are going to be good to plan a flight are shown here. So parameters related to thermals, so the strength of thermals, how high they're going, the depth of thermals. Clouds, what height cumulus clouds are going to be at, other layers of cloud, wind at various heights, atmospheric waves, and a whole bunch of experimental things. And there's a few more parameters and things that are kind of not shown on this screen. And at the top here is the time scale. This is between 8 AM and 8 PM. And this is just a snapshot, but I can click on any of those and it will give me a map of whichever parameter I select for that period of time. So it is really useful in terms of visualizing the data. One of the parameters is potential soaring distance. So this is for that same day. It shows, and this is the path that I actually flew. And it shows the scale on the right here is in kilometres, and it's colour coded, and it shows the potential soaring distance for a typical glider, typical pilot, how far they might expect to fly, which is showing about 800 kilometres or perhaps slightly less for that day. Now I'm flying a high performance glider, so it's not the typical glider. I would hope that I'm not a typical glider pilot either. And I also optimised where I flew, which gave me the extra 500 kilometres in terms of what this weather model was actually saying. I'll just quickly look at this. But it could also give you other views, for example, at a point that I've selected here, which is somewhere just a little bit north of Gawler, it shows the height that thermals are going to, the strength of thermals, the wind, and various other parameters in this case, 1 hour time intervals during the day. So just in a snapshot, I can see roughly when the thermals are expected to start, which is around about 10 AM here, and stop at about 6 PM. Although on a distance flight, even though the thermals stop at 6 PM, I'm probably going to be at, in this case, it's showing about 13,000 feet, and it was actually in reality a little bit higher. And it's going to take me something like 45 minutes to glide down from there. So even though the thermals stop then, you can actually come home quite a bit later. And this is really amazing. This shows the cloud base at 5 PM on that day. Now, this is the base of cumulus cloud, which is the lowest layer of cloud. In summer, if there is any, it's often no cumulus cloud. If there is any, it tends to be between 4,000 and up to 10, perhaps a little bit more than 10,000 feet. If you look at the scale on the right here, this purpley colour here is 15 to 16,000 feet, and it was accurate. So a whole large area of South Australia, running all the way into Victoria, had a cloud base of somewhere between 15 and 16,000 feet, which has huge advantages, as I talked about before, in terms of flying distances because of the density of the air at those heights.
Peter, what sort of notice is that? Is this like 12 hours in advance that you know this, or is it 24 hours in advance to know this information?
Yeah, so I watched this for a period, quite a period. So all of these models, they go out to about 5-6 days. So I can see it develop, and then they're updated initially a few days out each day, and then as it progresses, several times a day in the last day, which means that I can actually see what the model is saying well in advance, and then just watch how things progress as the days go on. And as most glider pilots will know, you pick a good day some days out in advance, and it just deteriorates as it approaches. But that's all modelled, and it's all accurate, reasonably accurate. I guess the other thing to point out is that these are models. It may not be what actually happens on the day, but as technology enhances and time moves on, they're getting more and more accurate. Okay, so really important for this flight was convergence, and the convergence that I was using to get the distance that I could actually get. So this is what SkySight was forecasting before the flight. The orangey, reddy sort of areas there are the rising air in convergences, and the falling or sinking air is the blue area. So as you can see, I followed this convergence heading down to the south here, down into Victoria. While I was down in Victoria and coming back out again, the convergence, as it does, particularly sea breeze convergence, moves progressively inland, which is why my track coming home is a little bit further inland than the track going out. So it moved a little bit further in, and I followed that along there. You can see the convergence line runs all the way up. In fact, you can't see it on the top of the screen, but it runs up to Port Augusta, and it keeps going down all the way to Tasmania down here, down to the southeast here. So I really spent a lot of time looking at where the convergence were, when thermals would start, a whole bunch of parameters to pick the time to take off, to pick exactly where I could fly, which is constrained by airspace as well, and constrained by COVID-19 restrictions, to really get the most out of the day. So this is a photo. It was actually not taken on that flight, and it was taken, I think it was January this year, photo I took in January this year. It is flying a trough line, and this is what commonly happens along a trough line, is that you get a lot of moisture being fed in along a trough line, and then you get overdevelopment late in the day and rain, which is what this is showing here. So this is the town of Burra, so some of the pilots might recognise that, and I'm heading south from Burra. Again, this was also a day with a sea breeze convergence. The sea, the Gulf of St Vincent's out to the right side of the picture here. So we're getting a convergence running along here as well. So it's a pretty similar day, but a lot more moisture in the air. I guess the other thing to note, if you have a look over here, very sadly, is a big plume of smoke. Well, that plume of smoke is more than 100 kilometres away. It's over the Adelaide Hills, and there was a pretty big bushfire that day. Okay, so more of what you can see on here is the instruments, of course, which are in a glider are relatively basic instruments, but they've enhanced over time. So I'm just firing something up in the background here. Come on. My moving map display is shown here. Now, a lot of these are actually integrated into the panel now. Mine is not. I've got the cheaper version, but it provides the same information. So that's a GPS navigation device. It has all sorts of gliding specific parameters, like how far you can glide and things like that as well. But what's really important for this flight is that it also, those weather models I've just been talking about, I can upload them to this device so that I can access them in flight, which is what I did in that flight in November. So I don't know if you can see that. I'll just put that up in front of the camera. So that's the same device you can see in the picture there. And on that device, I could see where the models predicted the convergence to be. I could then cross-check that with what the cumulus clouds were actually doing, and adjust exactly where I was flying, because it's really critical flying along convergence to be in the right spot, 1 kilometre off the correct line, and you're in sinking air or suboptimal air. So it really is critical being in the right spot. Technology has moved on, possibly even by then, but certainly since then, and that's getting more and more integrated into the instruments in real time. So as I mentioned before, these models of what the weather is doing are updated several times a day. And now it's possible to actually upload those models in real time when they're updated into your instruments, so you can get a later update. On this particular time, I had to do that before the flight actually started. The other thing you'll see on here is the antenna on the left and the right here. And that's kind of where I'll finish up with this in terms of talking about the technology of the tracking system, which is based on something called FLARM. So I'll just briefly show you a device, and if you just look quickly at the camera, I'm holding in my hand a device called a FLARM. This one was actually, it's European technology, but it's made in Australia about 15 years or so. The Australians will recognise that as an AusFLARM. And what you see in the image here is a newer version of that same, effectively that same device. It was originally developed for collision avoidance and primarily to resolve a problem in the European Alps, but of course it has worldwide applicability. And the problem there was a very high accident rate in terms of air-to-air collisions, and also collisions with obstacles on the ground, and they're looking at a way to resolve that. So what this device does, has a GPS, this is the GPS antenna here, so it knows its location, and it transmits that location over a relatively short range to other aircraft that are also equipped with a FLARM. Those other aircraft receive those signals because it encodes the position, the GPS position, and it can then detect potential collisions. A bit like TCAS, I guess, if you like, in commercial aviation, except that this is tailored to sporting aviation and originally gliding, but it's been enhanced since then, and tailored for low-speed aircraft, relatively low-speed aircraft, that spend a lot of time flying in close proximity to each other. So the really advanced algorithms for doing that. Coming along, so that was the mid-2000s, and then since then it's now integrated with ADS-B, or ADS-B. At this stage, ADS-B in only, it doesn't transmit the ADS-B location. It has in it a database of, it's not very useful in Australia, but certainly when you're flying in alpine regions, it has in it a database of ground obstacles. In alpine areas, they're particularly concerned about ski lifts and cables stretched across valleys and things like that, which gliders have a habit of running into. And it will warn pilots about those as well. So this device has been a huge improvement to flight safety. Used, well, it's now mandated in competitions as well, and it has reduced collisions significantly. And so the top left corner of this diagram shown here shows a glider and another aircraft, possibly light sports aircraft, but another aircraft, both FLARM equipped, which if they're both FLARM equipped, they can both detect each other and be warned of collisions with each other. And also with obstacles such as related to these mountains down below. Now, the innovation that's happened that enabled my flight last November to be tracked is the smart chaps that took this FLARM information, which is fairly short range. It's 3 to maybe 10. I have occasionally seen 15 kilometres, but generally it's sort of 1 to 6 kilometre range. It's pretty short range. But if you have a ground receiver, it can actually receive that signal up to, say, 150 kilometres. There's one of these receivers installed at Waikerie in South Australia. There's numerous others around South Australia, around Australia at the moment, and we're actually in the process of rolling out a bunch more in South Australia. So this ground receiver receives the location being transmitted by these FLARM-equipped aircraft, puts that into a ground-based network called the Open Glider Network, and then that can be made available to either other aircraft that are airborne through the OGN protocol, even if they're not FLARM-equipped. And also then, shown down the bottom here is any number of apps, and these are growing all the time, that then can display the location of, including height, of each of those aircraft. So the specific ones, I'll show you some snapshots of these in a moment for OGN, but also things like Flight Radar 24, Oz Runways, Airplan. There's more of these that more and more of these coming out that actually will now show gliders, in addition to normal sort of commercial traffic. So the next slide. Yeah, I'll show you some examples of that in a moment. In fact, why don't we do that? Now, this at the moment is, well, it's the middle of winter in Australia and most of Australia is locked down. So there's a little point in showing you an image from Australia of what this actually looks like in one of these apps. This was the last weekend, a small section of Germany. So it's about 150 kilometres or so across on the screen here. And all the yellow square things are gliders. And you can see an awful lot of them in a fairly small patch of sky. So you can see the advantage of having this. All of those are FLARM-equipped aircraft, and they have the collision avoidance system as well in them, so they can actually see if there are potential collisions. These little antennas shown, there's the green one here. I'm not sure what the significance of the colour is anyway, but green here where the cursor is, black, green, a whole bunch of them up in here. Now, there must be hundreds, if not thousands of them in Germany, worldwide, at least tens of thousands, and they're coming up all the time. I mentioned that this system was originally developed for the Alpine regions. So this is actually, again, last weekend, so last Sunday. It shows the density over the Alps. So this is France, the Alpine regions of France. So Nice, Monaco down there. And you can see very high density basically on the ridge lines. So that's why it's so important that they can maintain separation using FLARM. FLARM actually won a bunch of awards for those safety benefits going back more than 10 years ago. The other innovation, which is actually very recent and wasn't available back last November, is you can see this little tag down here. It says SkySight weather for 1300. So this is where there's a more integration of different systems. So in this particular case, it's SkySight being integrated with the OGM viewer, so you can actually see various views, but at the moment this is showing the height the thermals are going to at this particular instance in time, what the thermals are predicted to go to. And you can see, of course, glider pilots prefer to be high. So in this area here, they're actually staying high, where this colour shows that the thermals are actually at their best. Now, OGN is really a huge, well, FLARM, but also OGN, huge enhancement to safety, so much so that EASA, the European equivalent of CASA, gave the first GA Safety Award to OGN with a first prize of £8,000 back in May last year. So that really is an acknowledgement by broader aviation of this technology and what it can actually do for safety. Okay, just finishing up. I think this is my last slide. Yep. This is me sitting on the ground after a flight. Well, not me so much, but my glider. We are limited in Australia by last light, so we can't fly at night. Generally wouldn't anyway, but it's not safe to fly at night, and we don't. So on this flight, I needed to time my arrival back home to arrive before last light, because it's not safe to be landing at last light and not legal anyway. And so that's what I actually did there. It's actually a really enjoyable time of the day. So I mentioned before that I want to take the last thermal right to the top and then glide home from there. So I'm gliding for something like 40 minutes, coming down from 15,000 feet in 40 minutes, but it's at a time of day when the thermal activity, the thermal updrafts have actually stopped. The air at that time of day is dead smooth. So I just love that time of day. So it's flying, just cruising, feeling like you're a jetliner, gentle whistle. Gliders are not completely silent, but almost silent. Just the gentle whistle, cruising into a what we call a final glide for a landing back at Gawler. So I'll leave you with that photo, and I guess I'll open the floor up to questions. I'm sure there are questions.
Yes, thank you very much, Pete. And the first question that I've got is from Michael Cribbs, just asking what were the issues operating in controlled airspace for this flight?
Okay, so this flight, I remained out of controlled airspace for the entire flight. We can fly in controlled airspace, but generally it requires a transponder, and it requires pre-coordination with air traffic controllers. And for the most part, glider pilots tend to stay out of controlled airspace. And on this entire flight, that's what I did. So I didn't fly in controlled airspace at all. It was Class G airspace for the entire flight. That, of course, becomes a bit limiting in terms of the part of the sky I can fly in. But that's something I'm willing to accept.
Thanks, Peter. And I know there's still 133 people listening. Does anyone else have a question? Feel free to use the Q&A button at the bottom. Yep, I've got a hand up too, so. I'll see if I can find that hand. Okay. I've got another question from Peter Champness. You're coming from a very high and a long way out. What safety height did you program in to be sure of getting home?
I actually can't remember on this particular flight. So for the non-glider pilots out there, the safety height is the height that we aim to arrive back at the home airfield at. So we have a final glide where we're gliding back to the home airfield, and you could program in a safety height of 0, which means that if all goes well, the glider performs as it should, and you don't find any sinking air, you'll get back there at ground level, which is probably not a very smart thing to do. So we don't do that. We actually put a safety height in, and we aim to come home higher, so if something goes wrong, then you have a little bit of height up your sleeve, and you can still make it back to the home airfield. I tend to use something like 500 to 1,000 feet. I can't remember what I used on this day. It's not absolutely critical, because if we don't make it back to the home airfield, there are other places we can land. It's not very convenient, because somebody's going to have to go out and fetch me. But if I don't make it back to the aerodrome, the home aerodrome, I can land elsewhere. So if on a final glide coming in, like on this day, I'd found myself short of height. And of course, it was very late in the day, so there's not going to be any thermals to get any more height back again. Then I'll end up lobbing it in and landing somewhere a few kilometres, or maybe 10, 20 kilometres down the road. And that's a perfectly safe thing to do, and we do that. We'll try not to do it, but do it semi-regularly.
Thanks, Peter. I've got a bunch of questions now, so I don't know if we're able to get through all of them in time, but I'll take them from the top. How many kilometres could you have flown if Victoria was not in lockdown?
A good question. I don't really know how far I would have flown. I certainly would have continued my track, because that convergence line you saw in that spectacular photo did just keep continuing and all the way down past Victoria. I think I probably could have gone down to at least past Horsham, not as far as Melbourne because you're under controlled airspace, but certainly another several hundred kilometres. Possibly not a lot further, because I used the maximum part of the day before last light anyway. And it's a matter of staying in the best rising area and the best conditions. And I had pretty good conditions late in the day, even where I did fly.
Thank you, Peter. There are still a bunch of questions, but if in case the WebEx suddenly disappears at 7 p.m, I just want to thank you very much for an absolutely outstanding presentation. Wonderful communication of the technology, of the achievement, and outstanding imagery, and brought it all together really, really well. So, and I've seen a lot of positive comments coming back from people in the chat line on the right. So on behalf of the Royal Aeronautical Society, thanks for stepping up tonight and providing this talk.
Thanks for that, and it's good to see so many people enjoyed it. There were quite a few people online there.
I'll pick just another few questions as we go on. What would you do differently if you did that flight again?
I think in terms of where I flew, probably not a lot different. One of the things that's really important in gliding is I've done quite a lot of record flying before. This was not a record flight. Now, a record flight is one that needs to be pre-declared. So you actually say in advance, before you take off, where you're going to fly. You record that, and that gets analysed afterwards and determine whether you did that or not. On this flight, I didn't do that. So it wasn't pre-declared, and therefore is not eligible for any record. So if I was going to do a similar flight like this, then I would actually plan it out, pre-declare where I was going to go, and potentially gain a record. I've certainly got my eye on some flights out and return in similar sorts of conditions out to the north. So that would be flying from Gawler up to past Maree, partway up the Birdsville track, and then back to Gawler for a flight of something like 1,250 kilometre declared flight, which hasn't been achieved in Australia before as an out and return flight, and that's something I've got my eye on in future.
Oh, excellent. How much physical fitness training did you need to do in preparation for the long flight?
Oh, I'm a super fit person. Can't you see that? No, gliding is a mental activity. It's not a physical fitness activity. Yes, it's a 10-hour flight, and if you're in really bad form, then perhaps 10 hours of concentrating and is just not going to work very well. But I'm certainly, as my wife will attest to, I'm not a fitness freak. I'm not the fittest person around. But basically, I mean, you're sitting in a glider. The controls are relatively light. It's more about the mental abilities and the stamina to be able to keep it up for that long.
Excellent. Murray Stimpson wanted to know how useful were the satellite and SkySight overlays in flight when you had the big highway in the sky of cumulus clouds as real-time guidance?
Yeah, I did use them. Not as useful as you might expect, because I had the instrument showing me where the convergence should be, and I had the cumulus clouds showing me where the convergence actually was. Now, am I going to trust a model, which was done the day before, or am I going to trust what I can actually see in the sky with where the clouds are showing me as the lift being? So I did use a bit of both, but probably that modelling of where the convergences are is going to be most useful when there are no clouds indicating where the lift is, and then you might as well do something like follow what the model said.
Excellent, thank you. How much drinking water and food did you take?
As some people will attest to, I don't drink enough when I fly. I was carrying 4 litres, I think, and I drank most of that in 10 hours, which is actually not enough. It means I am actually dehydrated at the end of a flight like that, which isn't a good thing. I had a small amount of food, not a lot. You just need to keep the energy levels up. So just periodically, just to keep the blood sugar at a reasonable range, I just eat some dried fruit every hour or so, and a small bucket of dried fruit is more than enough in a 10-hour flight.
Okay, dried fruit and just 4 litres of water. Steve Miranda wanted to know what toilet system you used, but maybe you didn't need one.
Yeah, I knew that question had come up. I talk a lot about doing coaching lectures for people. And what I say to people is if you're not peeing in flight, then you are dehydrated, right? Particularly a 10-hour flight. So no, I can't do a 10-hour flight without peeing. If I did, that would be a very dangerous thing to do. So yes, I knew this question would come up. There are various toilet systems. There are various medical systems that I won't go into the details of. Some gliders have a plumbed-in system that ejects it outside, or we can just use plastic bags and just retain those on board. But yes, we do need to pee in flight.
Excellent. I have a technical question from Julie Lentil. What was the average McCready along the flight? Do you adjust this often during the flight?
Yes, I do. Well, that's quite a technical question that won't mean much to the anybody that isn't a glider pilot. McCready is actually based on a theory of cross-country flight from Dr. Paul McCready from the US in the 1950s, I believe. And he devised a theory as to what the optimal speed we should cruise at based on the strength of the next climb. So when we're actually flying, we're nominally flying a McCready setting, which is based loosely on our next climb rate. On this, that's a fairly old school way of actually planning our speed, and I don't tend to use it very much these days. I was mostly cruising at a more or less fixed speed of about 90 knots, a little bit slower if I was in rising air and a little bit faster if I was in sinking air, which probably equates to about a McCready 5, something like that for the glider pilots.
Okay, thank you for that one. You mentioned during the first 2 hours were a little marginal, and Daryl Burton saw from the trace that you were down to around 1,000 feet AGL. How touch and go was it?
It was pretty touch and go. It was one of those stages early in the flight where you kind of think, remember also it's 44 degrees. We don't have air conditioning in these gliders. When we're up at 15,000 feet, in fact, it can be close to, well, that day it was close to freezing, close to 0 degrees at 15,000 feet. No problem up there. But on a 44-degree day, when you're down near the ground below 1,000 feet, you're stressed, you're low, the conditions are difficult, it's really hot, you're sweating. It's a pretty uncomfortable situation to be in. You try and avoid it at all costs, but of course, you can't always avoid it. And on this particular flight, I was kind of thinking, and I know a few other people did abandon the flight on that same day. You kind of think, is it really worth all this effort? Or should I just turn around and fly home and have a nice cold beer? But I'm glad I did persist, because I got through that first few hours, and then the rest of the day was just astronomical. It was just magic. So I'm glad I persisted.
Fantastic. Alan Wilson makes a comment that we look forward to the day when CASA integrates FLARM into their radar surveillance for RPT awareness, and thought you gave a good promotion to that. Well,
yeah, whether CASA is going to do that, I don't know. I mean, what is actually happening in future is probably more the other way, is that more and more gliders will get ADS-B, ADS-B, and in particular ADS-B out, which means that we'll then be using a system that's compatible with CASA, which FLARM is not, and they'll be able to see us through that.
Okay. Just a few more to finish off, and I've got 4 to go. That's it. The first one, 4 to go. Any tips for a powered pilot who's just about to start to learn to soar?
Yeah, go do it. Have fun. Look, there's any number of clubs. I don't know where this person's from, but assuming they're somewhere in Australia. The Gliding Federation of Australia on its website has a list of gliding clubs. Approach one of those clubs. They'll put you, depending on where the club is and how they operate things, they'll either put you through a training course, which is the best way to fly, which will generally get people up to a standard of flying by themselves, solo standard, in a week or a bit over a week, particularly if they've got power experience beforehand. And then they just progress like on a weekend or something basis beyond that. But the first step really is contacting one of the local clubs and enjoy the experience.
Excellent. Is there a minimum separation between gliders in uncontrolled airspace?
Yes, there is, and it's 200 feet. Yes, 200 feet minimum. Yep.
Excellent. If you declared this flight, what distance would you have nominated?
I wouldn't have declared, yes, really good question, and I wouldn't have declared 1,300 and something kilometres. I might have declared 1,250, which I think might have been achievable. Probably not achievable without going down into Victoria, because another limitation in terms of doing a cleared record flight is you can't have too many legs in the flight. And this flight had, I think, 5 legs. So a few too many legs. So the only way of actually doing that longer distance is to extend the ends, which would push me into Victoria. So that would have made things a little bit difficult there as well. But yeah, I think a 1,250 flight like that declared would have been a good achievement.
Excellent. And just the two last ones from Garth Morgan. In what form is your glider imported from Europe? i.e. do you install and glass the wings in after delivery?
So it comes, gliders can be what's called de-rigged. So the wings actually are effectively bolted on. Same with the tail, which means that they can be, and the wings are actually in pieces as well. So there's 3 pieces to each wing, so 6 pieces total for the wings. And then they go into quite a long trailer, so a glider trailer. So when they come out to Europe, they come disassembled, and then we reassemble them, which is in Australia, which is actually a fairly straightforward, normal process to do. And any glider pilot can assemble and disassemble and reassemble the gliders.
Okay, thank you. And the last one out of left field from Ashok Kurana was, would you be interested in teaching how to teach at university?
I'm retired. I kind of like to stay that way, I think.
That's right. Enjoy gliding.
Yeah.
Well, thank you.
Anyway, I know Ashok, so I can speak to him afterwards.
Oh, good on you. Well, thank you very much. There has been so much positive feedback. Your presentation was so thoroughly enjoyed, and I appreciate seeing you and seeing the presentation. So thank you.
Okay, and thank you all for coming along. Stay safe.
Okay. That finishes the presentation. For those who want to come along next month, we've got a presentation by a gentleman from Bespoke Engineering to talk to us about a modern radial engine that was developed for aviation and is now a target of motor vehicle enthusiasts. So that'll be on the 26th of August. Thank you very much and good night.
Good night all.
Good night.